this video, we are going to study my favorite theorem from real analysis. Recall that the classical Weierstrass theorem says that any continuous function on a closed and bounded interval in R can be approximated uniformly by polynomials. In real analysis 1, we have seen a proof of this using Bernstein polynomials. Now, we are going to see a more abstract and general version of the Stone Weierstrass theorem that not only greatly generalizes the classical Weierstrass theorem, but it also gives a new perspective into the classical Weierstrass theorem. The proof of the Stone Weierstrass theorem will require a basic version of the classical Weierstrass theorem in one step, but apart from that, the proof is completely self-contained. So that one step, if you could give a self-contained proof, this Stone Weierstrass theorem at one shot gives a proof of a very general type of Weierstrass theorem. So without further ado, let me just state the theorem. A bit of terminology is involved. I'll try to keep it very basic. So here is the theorem. Let X be a compact metric space. So as you can see, from a closed and bounded, that is a compact interval in R, we are jumping all the way to a compact metric space. So let X be a compact metric space. Equip Cx, the space of continuous real valued functions on X, with the sup norm. So this is our favorite metric space. Let S subset of Cx be a vector subspace. So we are considering the collection of all continuous functions on X, and we are considering a vector subspace S. That means the sum of two functions in S is in S, and lambda times F is in S if lambda is a real number, so on and so forth. With the additional property that if f comma g are in S, then fg is in S. Okay, so let me just list out. I need three different properties. So with the additional properties, let's make it properties. With the additional properties that number one, if f comma g are in S, then the product fg is in S. The product of two continuous functions is continuous. So we are requiring this vector subspace of Cx to also be closed under multiplication. In fancier language, this is essentially going to make S into a subalgebra. S will be both a ring as well as a vector space, and the operations between scalar multiplication and the product will behave well. So I'm not going to state the more general definition of an algebra. You can look it up in any standard textbook or Wikipedia. Okay, so the product of two functions is also in S. Number two, all constants are in S. Any constant function is automatically continuous. I'm requiring this subalgebra S to contain all the constants. And number three, this is a crucial property. S separates points. What do I mean by this? If x comma y are in X, there exists a function phi in S such that phi of X is not equal to phi of Y. No matter what pair of points x comma y you choose in X, you can always find a continuous function phi in S such that phi of X is not equal to phi of Y. Now, under these conditions, the conclusion is then S closure is equal to X, not X, C of X is C of X. So what this is saying in more down to earth language is any continuous function on a compact metric space can be approximated uniformly by functions coming from S. Now, the first order of business is for you to pause the video and check that indeed the set of polynomials on a closed and bounded interval indeed satisfy all these three properties. So in some sense, that's a sanity check to check that this Stone Weierstrass theorem in fact generalizes the classical Weierstrass theorem. Okay, so we have to show under these abstract conditions that S closure is equal to C of x. And the proof of this is not hard and it's extremely elegant. We proceed step by step. So let's go on with the proof. So I'm going to draw a bad picture as usual, but this bad picture is going to serve as a nice intuitive guide towards the proof. So I'm going to draw the xy plane, even though this set x could be anything. And let's say for simplicity's sake, we are going to take x to look like this, and we have some continuous function. Okay. Now, what is it that we have to do? So this is what we have to do. Fix epsilon greater than 0 and f in Cx. Goal is to produce G in S such that f of x minus epsilon is less than g of x is less than f of x plus epsilon for all x in X. You agree with me? What we have to do is we have to look at this epsilon width neighborhood of this function, something like this. In this epsilon width, we have to find some other continuous function that lies entirely within this epsilon width. And this epsilon is completely arbitrary. For a fixed epsilon, we have to find a function g which is squeezed in between f of x minus epsilon and f of x plus epsilon. So we are going to approach this by divide and conquer. Let's first try to show that we can find a function g that satisfies this. G of x is less than f of x plus epsilon. Okay. Now, what I'm going to do is I'm going to make an additional assumption, and I will sort of highlight how to remove this additional assumption towards the end of the proof. I'll give a sketch and you complete the proof. So what we are going to do is we are going to make an additional assumption, which is key. Additional assumption. The additional assumption is as follows. If g comma h belongs to S, then max of g comma h and minimum of g comma h are both in S. Note that the maximum and minimum of two continuous functions is automatically continuous. If you cannot see it immediately, please pause the video, spend 5 to 10 minutes and figure out why the maximum and minimum of two continuous functions is always continuous. So we are going to make this additional assumption about S, and towards the end of the proof I will highlight how we can get rid of this additional assumption. In fact, it is this getting rid of this additional assumption that actually requires the classical Weierstrass approximation theorem. Okay, so I will just briefly say that by induction, the additional assumption guarantees that the max and min of finitely many functions in S is also in S. So you can show that the maximum and minimum of finitely many continuous functions is continuous. What we are requiring of this subalgebra S is that it is not only closed under multiplication and addition, but it's also closed under taking maximum and minimum finitely many times. So this second part, this by induction, is rather trivial. You can just skip it. It's so easy. Now let's proceed to the original proof. We want to show that given a fixed epsilon and a function f in Cx, we can squeeze a g in between like this. Now, what is the only thing that asserts the existence of functions about our algebra S? If you notice, the first condition does not say anything about existence. It just says that given two functions f and g, you can combine them, and that will also be in S. We know that all constants are in S, which is a good start. We also know that S separates points. Okay, so the fact that S separates points tells us that there are plenty of continuous functions. In fact, it says that given any pair of points x comma y in S, there is at least one continuous function that separates them. So that sort of generates for you a number of continuous functions on S, and we are going to exploit the existence of these separating functions. So what you do is the following. Fix x comma y in X. Then we can find a function phi of x, not phi of x, phi in S such that phi of x is not equal to phi of y. This is just rewriting. I'm writing the entire hypothesis again. Now what you do is consider alpha comma beta real numbers. Fix two real numbers alpha and beta, or rather let me just say fix alpha comma beta in R, and consider the function h of x comma y, which is by definition equal to, let's see whether I can get this right, it's beta minus alpha plus alpha times phi of z minus phi of x divided by phi of y minus phi of x. Okay, so what is this trying to say? What am I trying to do? Well, this is what I'm trying to do. Let's go back to our picture. We want to squeeze in this function g within this grid sort of thing centered on the function f. So what I'm going to do is I'm going to proceed step by step. I'm going to fix points x comma y. I'm going to fix points x comma y, and my aim for the time being is to just construct one function in S that agrees with the given function f at the points x comma y. So the goal is I need to produce a function that is very close to the function f. As a start, what I'm going to do is I'm going to produce a function hx comma y which agrees with f at these two chosen points x and y. That's the aim, and the claim is that this function does the job for us. This function does the job for us. How does it do the job for us? Well, let's see what this function's value is. First of all, h of xy is an element of S. Okay, y. Please check that. Why is this an element of S? Now, what is this function's? What is the special feature of this function? At the point x, of course, this is a function of z, so I must make that precise. At the point x, note that you get in the numerator phi of x minus phi of x, so the second term vanishes, and you are left with beta minus alpha. Okay, and at the point y, what happens is, let me just change this slightly. This is not what I want. I want alpha plus beta minus alpha times this. Okay, this is what I want. Now let's say at x comma at the point x, this thing vanishes, so this whole thing vanishes, so you will end up with alpha, so this is just alpha, and similarly hxy at y is beta, right? Because this quantity becomes phi of y minus phi of x by phi of y minus phi of x, which is just 1, so this is alpha plus beta minus alpha, which is just beta. So what have we achieved? What we have achieved is, given two points, x comma y and values alpha comma beta, I can find a function hxy in S such that hxy of x is equal to alpha and hxy of y is beta. So no matter what 2 points I choose in x and what 2 values alpha comma beta I choose in the real numbers, I can always find a function in S that at least agrees with, sort of interpolates hxy x equal to alpha and hxy y equal to beta. Okay, now for any pair x comma y in X, denote by hxy the function in S such that a function in S, it may not be unique, a function in S such that hxy of x is f of x and hxy of y is f of y. And the previous argument just shows that such a function hxy exists for every pair. Note, if x equal to y, this is trivial. You don't need to use the previous argument. Okay, y. Okay. So what have I done? Given a pair of points x comma y, I can find a function hxy that agrees with f at the points x comma y. Now here is the part where I'm going to use that minimum and maximum business. Fix x in x. Now the goal is to at least satisfy this second inequality. To produce a function g that is not too far above the function f. It is lying below f of x plus epsilon. Okay, how do I do that? Fix x in x, then for each y in x we can find a function hxy as above. Okay, now let by be the neighborhood or a ball centered at y such that hxy of z is less than f of z plus epsilon for all z in this ball by. Okay, what am I saying? Well, we know that hxy of y is equal to f of y. What I'm saying is choose a small ball, call it by, centered at y, such that hxy of z is less than f of z plus epsilon for all z in by. Why can I do this? Well, just consider the continuous function hxy minus f. This function is 0 at the point y. Therefore, by the standard epsilon, whatever definition of continuity that you like, you can find a ball such that hxy minus f is less than epsilon in that ball, which is same as saying hxyz is less than f of z plus epsilon. Okay, so this is just a standard basic continuity argument. Because h and f agree at the point y, I can make h not too far above f, at least in this ball by. This can be done for each y in x, right? For each y in x, I have fixed x, remember. For each y in x, there is a function hxy. Corresponding to this point y, there is also a ball by, such that the function hxy on this ball by satisfies this inequality. Okay, so this is all fairly straightforward. This is just using the basic properties of continuous functions. Consider hx by definition is minimum of, oh wait a second, I jumped. By compactness of x, we can find y1 to, let's say, yn in x such that by1 comma dot 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 byn cover x. So I'm going to be very, very brief here. This is a standard compactness argument which should be second nature to you by now. We can find finitely many balls by1 to byn that cover x. Okay, look at the corresponding functions. Define h of x, by definition equal to minimum of hx y1 comma dot 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 hx yn. And by that induction and the additional assumption, this hx is an element of S. Okay. Now what is the special feature of hx? Well, it satisfies hx of z is less than f of z plus epsilon for all z in x. Okay, check this. This is a trivial check. By taking minimum, we have more or less forced this to happen. In fact, because we want this to happen, we have taken the minimum of the functions hxy1 to hxyn. Okay, so as a recap, we fixed x, varied y, and obtained these functions hxy1 to hxyn. We took the minimum, we have got a function x. Now we repeat the same trick again. For each x, we get a function. We get a function hxz as above that satisfies. We have forgotten the point x, so that's feeling a bit lonely. Satisfies hxx equal to fx, right? Note that all of these functions hxy1 to hxyn satisfy that hxy1 of x is equal to f of x, comma dot 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 hxyn of x is also f of x. By taking the minimum, we are not doing anything, so we still have this hx of x equal to f of x. Okay, and for each x we can find a function such that hx of x equal to f of x and hx is not too far above f of z. Okay, now we pull the same trick again. Define g to be max. Okay, again I'm skipping a step. What we do is the following. By continuity, we can find a ball bx such that f of x minus epsilon is less than, f of z minus epsilon is less than hx of z for all z in bx. Okay, so we can find a ball bx centered at x, centered at x, such that f of z minus epsilon is less than hx of z for all z in bx. This is the same continuity argument again. By using the fact that this function hx and f are both continuous, this is rather straightforward to see. Okay, now by compactness we can find points x1 to, let's say, xk such that bx1 comma dot 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 bxk cover x. So for each x we can find a ball bx such that this happens. The collection of all such balls cover x. There is a finite subcover. Choose x1 to xk such that bx1 to bxk cover x. Now we are almost done. Set g of z by definition to be max of hx1 z comma dot 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 hxk z. Okay, then by construction f of z minus epsilon is less than g of z is less than f of z plus epsilon for all z in x. Okay, so this completes the proof. please ponder over the proof for some time to understand what is happening. It's just rather you do the most straightforward and obvious thing and everything just works out. Now we have to justify getting rid of the additional assumption. Okay, we have to get rid of the additional assumption. What did the additional assumption say? It says that if f comma g, or rather g comma h, are in S, then we assume that max of g comma h and min of g comma h are both in S. Okay, this is not quite always true, but we can get rid of this quite easily. What we do is the following. First of all, observe that max of g comma h is just g plus h plus mod g minus h divided by 2. Okay, I think this whole thing is divided by 2, and minimum of g comma h is g plus h minus mod g minus h, the whole thing divided by 2. Okay, let's see, is this correct? Max gh is g plus h plus mod g. Yes, indeed it is correct. So please check that these formulas for the maximum and minimum of g and h are correct. I think I have done this once before in real analysis 1. If not, it's a straightforward check. Okay, so we have explicit formulas for g plus h, max of gh and minimum of gh. Now observe that because we are in an algebra, S is actually a subalgebra, if you could show that modulus of g minus h is in S, you are actually done. So what we will not prove is not that will not be true for any subalgebra that satisfies the other properties. What I'm going to show is I'm going to claim if f is in S, then mod f is in S closure. I'm going to show this instead. Then I'm going to leave it to you to see that this claim will immediately get rid of the additional assumption. That additional assumption is not really going to make that much of a difficulty for us. Okay, so I'm not going to give the full proof intentionally. I'm going to leave a bit of thought to you. I'm going to show that if f is in S, then mod f is there in S closure. Okay, how do you show this? Well, f is first of all a continuous function. Therefore it is bounded because x is compact. Therefore it is bounded. So we have minus c less than or equal to f of x is less than or equal to plus c. C is greater than 0 for all x in X. Okay. Now what you do is observe that the absolute value function on the closed interval minus c is uniformly approximated by some polynomials. Let's say Pn. So we have Pn converges to the absolute value function on minus cc. Okay. Now because S is an algebra, Pn with the variable x substituted by the function f. Okay, I will leave it to you to figure out what this means. This is, if you have taken any course on linear algebra, this should be obvious to you what it means. Pn with the variable x substituted by the function f converges to the absolute value of f on x. Show. This is trivial. Show this. Okay, so this shows mod f is there in the closure, is in S closure. Okay, use this to finish the proof. So I'm intentionally leaving a number of simple checks for you so that your understanding is thorough. This will be the common theme for the rest of the course. A number of such things which will not take more than 15-20 minutes for you to do on your own. I'm going to leave it to you so that we can concentrate on the more difficult material. So this concludes the proof of the Stone Weierstrass theorem. There are some analogs of this and some exercises in the notes. Please go through them and solve them so that you have a solid understanding. This is a course on real analysis, and you have just watched the video on the Stone Weierstrass theorem.